Okay, welcome everybody. This is our second to last meeting for this semester, and after a big gap, the last one was a month ago, and then we had this very adversarial NeurIPS deadline that was unusually early. So I think everybody, most people might have been busy with that, but hope that it went well for everybody. And now I'm really excited to have Fernando Rosas join us today. We're going to talk about world models and his paper AI in a Vat. But before that, Fernando, do you mind if I ask you to tell us a little bit about your background and research interests? And especially, I think you are very interdisciplinary and you have done a lot of cool work in totally different things. So, how do you do it? Tell us a little bit about that.
Well, my first advice is if you can avoid interdisciplinarity, avoid it. Only
Oh,
do it if you cannot help it. That's my take. Because
okay.
I feel that all the infrastructure is against it, even if people
Mm,
say they are supporting it, but in reality, it's always going a bit going against the current. But if you cannot
mm,
help it, then you have to do it. And the other thing is that from the outside, it feels very promising. It's like, oh, we're going to combine this with that, and going to
mm.
kill cancer, but it's actually hard, you
Oh,
know.
yeah. Yeah.
So,
Well,
but yeah, like I cannot help it. I feel
mm,
that another thing that I find important is to kind of clarify what are your trade-offs. So between
mhm,
risk and kind of, like exploitation, exploration. So for
mhm,
me, I like taking risks and I like changing things that I do, and I know that there are cons in that, but there are pros, and I embrace them. And so my end suggestion is find what are your priorities and follow that. Yeah, my
well, I
background
guess that
is
makes
extremely.
yeah.
Mm.
Sorry, go ahead.
So I started life like education as a musician, and I did music composition. Then I did philosophy. I got completely confused after that, and then I did pure math to deconfuse me in irrelevant things. And then I did a PhD in electrical engineering to do something practical that I could touch,
Hmm.
which was
Hmm.
good. After that, I got completely enchanted with complexity science. So I slowly switched to complexity neuroscience, but all
Hmm.
kind of combined with my previous life on telecommunications.
Hmm. Hmm.
And I did that for quite a bit. And more recently, I got, as most people, I presume, equally excited and terrified with AI. So I'm now completely refocused into AI safety and alignment, which
Hmm.
I think of it as neuroscience of robots instead of neuroscience of humans. It's like very
Hmm.
similar questions to the ones that I have been pursuing, but in a different context
Hmm.
where there's a bit more of control. You can do experiments a bit more easily. It's still very challenging, but at the same time, I'm very optimistic that anything you can learn from McIntyre or related, then maybe can be translated back to neuroscience.
Hmm.
So that's where I am at the moment.
Okay, thanks for sharing that. I'm somehow not surprised at all that you started from music, then philosophy, then electrical engineering, now AI. And okay, so I don't want to linger too much on that, your early caution that you gave us, but do you mind elaborating a little bit? I mean, you said that you should do it if you are, kind of um, if you feel like you cannot not do it, right? That's my reading of it. So that's like you're basically saying that just follow your interests, and if your interests involve being interdisciplinary, then go for it. And I think I can understand why it's difficult because I mean there's maybe more of carving your own path involved than more of a traditional paths. But maybe I would add that, do you think that with very powerful AIs, it actually might be a lot easier to be interdisciplinary or even be a polymath now that we have those tools that can help you learn a lot faster and contribute a lot faster?
I don't. It's a good question. I don't know. It could actually be the
Mhm.
opposite. Who knows? So
Mm,
I had a funny experience that I did music and then math, and I did them in
mhm.
sequence. And a very
Yeah,
close friend of mine did them in parallel instead of sequence.
yeah.
And I find it very hard to think how the hell he did it because for
Mm,
me, what I have done is that I do one
mm.
thing at a time. I go very deep, and then I switch.
Ah,
So
mm,
and then I leave enough time for my brain to coalesce into something that then it stays. So my
mhm,
fear is that with AI, everything is so easy and quick that maybe
mm,
it's more hard to get things to stay. Uh,
Mm, mm,
but my take is that AI is not going to make it like for sure easy, but there's something about self-discipline that I
mm,
think is going
mm,
to be the key. Because you have all the
mm,
options, but how do you stay in the topic for long enough
mhm,
until the thing kind of, take a shape into you such that it will never go away? And
mm,
how do you tell when is the moment to move? Those are kind of
mm.
hard questions, and I feel
Yeah.
from what I have spoken with, people usually say that they find me unusual, that I have a good sense for that, and that they
Mhm,
find it very hard, you
mm,
know.
mhm. Yeah.
So I think that's sort of a very, very difficult thing that I do it by instinct. So I would find it hard to suggest how to do it. But yeah, but I think that's a very key thing because if you move too quick from one
Mm,
point to another, you end up with
mhm,
nothing.
mhm,
And I have
mhm,
seen
mhm.
people that do these PhDs into super interdisciplinary thing. They do a lot of everything,
Yeah.
but a bit of nothing. And at the end,
Yeah.
what do they know? Like, and I, I read a book years ago about music, and there was a guy
Mhm,
saying there is something you can do if you focus a lot and you do it, but there is
mhm,
something you can
mhm,
do if you wake up in the middle of the night by a fire alarm and you can still do it. So
mhm,
those are the things
mhm,
that are part of you. And
mhm,
I can see that if you go too quickly between things, you end up with
mhm,
nothing at that level
mhm.
of. So
Oh yeah,
that's
that makes perfect sense. I mean, you just gotta wait up, give it enough time to kind of marinate the ideas, and maybe there's no shortcut around that. So maybe this AI augmented research could help with certain aspects, like checking some derivation real quickly, and then doing some bootstrapping in terms of your learning. But maybe it seems like there's no shortcut otherwise in your own understanding, and that's something to be mindful of. Yeah, that's great to make it concrete like this.
the other analogy I found super useful is from David Krakauer. He used to say
Uh-huh.
that like cars make you go far away, but they make you physically weak.
Mhm.
Bicycles have the same purpose, but they make you strong. And like how can you use AI as a bicycle and not as a car? That's
Mm,
sort of something I find interesting to
it's a
think about.
supercharged bicycle. All right, this is great. Thanks, Fernando. So one more question before we actually jump into the paper. Recently, there's a lot of these, interest and curiosity around consciousness. Are these LLMs conscious, and can we build consciousness in silico, and all of that stuff? Do you mind sharing a little bit of your own takes on this? Because I've seen you are actively talking about this on social media. So,
Yeah, so we have a big paper coming,
ah,
and I think we have sort of a good answer to that, which is
hmm,
it's a meta answer, not an answer.
hmm,
So
hmm,
one thing is that I guess it's a personality trait. So I see a lot of people in academia that they stay with the
hmm,
same idea for years and they become more
yeah.
confident over the idea just because they stay on it. And I'm sort of the opposite, and I'm sometimes get a little bit frustrated when I see people very sure about something that I know is not necessarily true. So, for
Mm,
example, when computer scientists, because of their from background, they take completely for granted that computational functionalism is true or the physical
mm,
Turing hypothesis is
mm,
true. Like, who knows if it's true or not, but I would not take it for granted. So these are
yeah.
the kind of things that every time I see them, some part of me
Hmm,
comes like I should push back to bring a bit
hmm,
more of epistemic humility into
hmm,
the
hmm,
world. And so the proposition that we are going to put forward is something like not so much giving you the answer, but because I don't think nobody knows, like for
hmm,
sure.
hmm, hmm,
But there are a number of answers, and you can do some kind of Bayesian mixture on them.
hmm, hmm,
So what we think is very useful is to think, imagine kind of a thought experiment. You build a thing that is like as a human at a certain level, and you know humans are conscious. So what is the level that allows you to say, because this level of similarity, then this other thing is also conscious? So
hmm,
is it
hmm,
behavior enough?
hmm, hmm,
And I think most people would say no, obviously no.
hmm,
And some people say
hmm,
yes, but some people would
hmm,
say no. And
hmm,
then if behavior is not enough, what else do you need?
hmm, hmm,
So then the level two is to say you need the internal computations to be the same, which is computational functionalism, which sounds reasonable from some side. I used to think like that. I don't think so much about it anymore. And
hmm,
then what else could it be? And then you can start asking like causal structure. Maybe you
hmm,
need some kind of autopoiesis or
hmm,
the right environment. There are a number of requirements that you can become more and more stringent. And so
yeah.
our proposition is a bit like learn about all these alternatives,
Hmm, hmm,
become aware that there are reasonable people believing on them, so none of them
Mm-hmm.
is
Mm-hmm.
dismissible as stupid. And
Mm-hmm.
then our suggestion is put some kind of base and weighting on them, not don't choose
Mm-hmm.
one. So I have my personal kind of bell curve over so
Mm-hmm.
around the causal structure, I would say, between causal
Mm-hmm.
structure and uses.
Mm-hmm.
And but and so the what we're trying to do, the idea is to kind of clarify the options so that at least we
Mm-hmm.
can dialogue in a better way.
Mm-hmm. Mm-hmm.
And yeah,
Okay, that's great
no,
because I think I should confess that I probably am in one of those groups that just by default assumes computational functionalism, and to be honest, I don't even know what that means. So I'm actually looking forward to read your paper because I know that you're going to clarify it rigorously, so I can finally say that I understand it. And I think one knee-jerk reaction against the alternative proposals that reject this is that it just sometimes sounds like there's like these like consciousness particles that God is sprinkling to the brain or something. So it may be just a straw man, that criticism, but I agree with you that we at least we have to be clear about what is on the table and then like clarify which ones can be addressed scientifically and which ones cannot be, which ones are beliefs, which ones are hypotheses. Anyway, I
yeah.
think that's great. Yeah. So do you have a timeline for that paper coming out or
I hope it's a matter of weeks, but
weeks?
not more.
Okay.
In worst case, a month or not more than 2 months. And,
Okay.
and and just
Excellent.
to close with one thing,
Yeah. Okay.
I feel that consciousness is an umbrella of things, and some people
Yeah.
confuse. So they say, "Oh, if I have a word model and a copy of myself in the word model, that thing is conscious."
Mm-hmm.
Uh, that's one thing, but that doesn't imply that you feel pain, like proper pain, not a reward function
Yeah.
that you're optimizing, or
Yeah.
that you have metacognition, or many other things. So I think another thing that would be useful is to kind of decompartmentalize consciousness into more specific things, and then
Mm-hmm. Mm-hmm.
what is essential for that. Or
Mm-hmm.
so.
Mm-hmm. All right, that's very exciting, and thanks for sharing your thoughts with us. This is very, very fun. And with that, maybe we should now switch to talking about the actual paper. And before we start, I should just mention that these meetings are recorded and we put them on YouTube so that everybody knows this. Of course, with your permission, Fernando. We have this last few minutes where we stop recording and have a Q&A session. That if you have a question that you think, I don't know, is a hot take or whatever, you want to keep it for that, feel free. But if you have a question during the meeting, we always encourage people to actually interrupt. And so this is more of like a discussion, if you're okay with that, Fernando.
Absolutely. I would like to
All right.
know how long should it be because I think I
Oh,
have too many slides.
okay. All right. So the official time is that we are now 20 minutes into the meeting, and then the meetings run for about 2 hours or a little more.
Okay.
So there's on my side, there's one hard cutoff, which is like 45 minutes after the 2 hour mark. But I think I can make it. So
Yep.
yeah.
Good. I think we should make
All
it.
right. Cool.
Yeah, and super happy to take questions at any point. So please just stop me whenever that is useful.
Perfect.
So should I share my screen?
Yes. Yeah, let me see if I can make you co-host.
You have to allow me, yes.
It should work now.
Yep. Can you see my slides?
Yes.
Yep. Cool. So the plan today is to talk about this paper about the word models. So the main part of the paper will be discussing this. Sorry, the main part of the talk will be discussing this paper. But if we have time, I will present some extensions that we have been working more recently. So before starting, to acknowledge my great collaborators from different institutions and also the support that make this research possible. So what is the plan for today? First, clarify what is the problem setting that we're going to think about. Then put forward some fundamental ideas over which everything builds. Then we're going to talk about minimal word models, then interpretable word models, and then extensions. And the extensions are long, but we will see how far we get into that. So what is the problem? The problem here is about sandboxing. So the idea is that somebody builds a system, an AI system, and give it to you, and you don't know how it was built, you don't know the internals, and you have to verify it before deployment. So what do you do? And one idea is that maybe you could put it inside a simulator, like a black box that you can build for the agent so that the agent start doing things and you can test it. And hopefully you can use that to thoroughly test the behavior of this robot so that you can be sure that it's safe before deployment. And the super strong assumption that we're going to make is that we can build such a world model. That means that for every perception that the agent receives, sorry, for every action the agent makes, we can make a reasonable perception that will correspond to that so that it's kind of natural for the robot. This is a big assumption, but we're going to make it for the sake of the theory. And the interesting point is that even if we assume that this is true, the job is not done. So what else could we do even if that is true? So for example, one thing is that the model could be too detailed. So what if we have a quantum level model of the whole universe? That will work, but that's a waste, right? So maybe we are over simulating stuff that is not necessary. What about if the agent lives at a given level? So it's a classical agent, we don't need to simulate quantum mechanics. Or what if the agent is not very powerful, is located in a room, so a little bacteria in a room, we don't need to simulate the physics in the next room. So from here, the intuition that we take, the intuition pump, is this thought experiment called the brain in a vat. This is an old story from philosophy, but has kind of predecessors in all sort of genre. The idea is if we take a brain and we read the motor cortex, so the brain is kind of wants to do something. So you read the signals, you feed them into a computer, you generate sensory information that goes to the sensory cortex. Can you do that processing in a way that the brain cannot tell the difference? And the whole story in the brain of that is this possible? Is it not possible? Yes, no, why, etc. So here the interest is not to discuss about brains, but about AIs. So can we put the AI in a vat? So to do the same thing, we read the outputs, we process in a way that we generate new inputs in a way that the AI would be indistinguishable from the real world. Why this thought experiment is interesting or useful, I think there are two reasons. One is a computational question. How is the most efficient way to do that simulation? How can we do it with the minimal amount of computational resources? And the second question is, can we use that as a way to characterize how strong or weak the agent is? Because once you simulate the minimal world that the agent needs, if the simulation is very large, that corresponds to an agent that is very powerful. If the simulation you need to run is actually not so powerful, that means that the agent is not so. So in a way, the minimal world that an agent needs will say a lot about the agent and their capabilities. So that's another epistemic reason for doing this exercise. And in the whole paper, we divide the question in different directions. So we think about model reduction in the absolute terms, and this ends up in a weird story with negative probabilities that we're going to get into. Then the second direction, that is models that can be used online by the agent, and this ends in a different answer that is called the epsilon transducer, and that I claim is going to be useful for interpretability. And then there is another branch where we generate models that can be run back. These are we call retrodictive models or reversible models, and this could be used for interpretability of a different sort. For example, you could set the world in a state of doom, and then you can run it back and say what was the action of the model that was key in order to push the world into doom. So you could do more simulations backwards, and we have a whole math like development in the paper on what are the conditions for worlds to run backwards, etc., etc. I will not get into that. So today we're going to study the first branch about compression and the second branch about beliefs. So that's the plan. Now to study this model reduction, we are going to bring some key ideas. The first idea is the notion of an interface. So the idea is that we have an agent interacting with the world, but in reality, we're not going to care so much about the agent or the world. We're going to care about what are the actions that the agent can do, what are the perceptions, the observations that the agent can receive, and how these two things relate probabilistically. So we're going to define formally an interface as a collection of probability distributions. So here the notation, every time you see a bold letter, that's a vector. Every time you see nothing and two dots, that means from minus infinity or from zero up to t. Whenever you see dots with nothing by both sides, it's like by infinity or from zero to infinity. So basically, this is saying that we're going to require something like like a causality condition. So the outputs that happen from time zero to t, condition on the infinite history of actions, depend only on the action that you have done up to time t. That's the only condition we're going to impose to interfaces. And also the idea is that you have multiple probabilities for different lengths of outputs, and you want them to be consistent. So that if you marginalize one, you get into the other one. This is an interface. The interface doesn't say how the world works, it says how the agents see the world. So I like thinking, imagine you're kind of seeing a room through a very narrow window. That's your interface. You see very little, you can act and you can see reactions of that, and that is all captured by the interface. Now, if you try to simulate an interface as a graphical model, you end up with something like this. So for a given sequence of actions, you need to generate a given sequence of observations. And as you can see, this is not very scalable, right? So this is basically a very big conditional probability, and the longer the sequences, the longer the probabilities, and this is going to explode in your face exponentially. So here is where word models come in. So the word models make this graphical model computable. And the idea is that we are going to, so what is real, quote unquote, is the green and the red. So the actions and the observations. We're going to imagine, like take out of our pocket a blue time process that is this S. And this is completely out of the blue, but what we are going to require is that if you put the S into the picture, suddenly you can factor the conditional probability into these products of kernels. In principle, we could allow the kernels to change over time. For simplicity, I would think they're constant, so maybe they are just the same kernel, but we can also be very general. But the core idea is that the graphical model from the left, that is quite non-scalable and is completely implementable, turns into the graphical model on the right. And that means that the blue is serving as a Markov blanket from everything that happened before to what happens after. So the world model is the first thing is sort of Markovian condition on actions. And the second is that it's a sufficient statistic for everything that happened before into modulating how things will happen after. So, and the claim is that anything that satisfies this equation is a word model. And the key point is that a given interface can be modeled as coming from a lot of word models. So there are many word models that are compatible with the interface, and the agent in principle could be using any. And then the rest of the talk, we're going to look for reasons of, oh, this one is special because it's small. This model is special because it can be computed online, etc., etc. But this is the definition of what a word model is. Now,
Can we clarify the nature of these blue variables a little more? Because in the one of the previous slides, you said that we're not going to even focus on what's inside the agent. It's always this talk is about the interface,
yeah.
and we haven't entered the mind of the agent yet. And you're
Mhm.
saying that this is for you, this is the definition of a world model. But for
Yeah.
me, it seems to be it has to be an internal model of the agent that allows it to make predictions about its own consequences of its own actions. So it seems like how can you define world model without entering the agent? Does
Yeah,
that
that's
make
a very
sense?
good question. Yeah, yeah, absolutely.
Okay.
Let me answer it in the next slide. I think the next slide
Okay.
will, and we can come back to this point, but that's a very, very good point.
Okay.
So just before finishing this slide to say that in modeling, in considering this construction, how smart the agent is not entering to the picture. What is the architecture of the agent doesn't matter. What is the policy doesn't matter. It's only about the interface and factorizing the interface. So now, um, let me try to answer the question right now. We're going to go deeper into it later. So I'm thinking a bit more general definition of what a word model is. So in a literature, in some corner of RL or in a big part of RL, word model means things that the agent can build so that it can plan without trying, right? So you can do imaginary rollouts, and you can, especially when there are traps in the environment, is great because you don't need to fall into every hole. You can kind of imagine what you're doing, and then you learn a policy, etc., etc. Here we're taking a bit of a more general view. So a word model could be in the mind of agent, or it could be in the mind of the simulator, like the external person that is sandboxing the agent, and then is running the system to keep the agent happy in the world that is indistinguishable. That is also a word model, and that could be uncomputable by the agent. Is running outside of the agent fitting the thing. So there's a bit like simulation hypothesis kind of thing. And all of these are going to be called word models. And later, we're going to be able to discriminate between different types of word model depending on which of these arrows are present and which are absent. Does that
Wait,
help?
isn't that just the world?
And no, because the word has to be real.
Uh-huh. Okay,
This
I
doesn't need to
see.
be real.
Wait, okay, so world model in this case is just it refers to the fact that it's just a model. It's a simulation, not a real world. It's not
Yeah.
referring to the Kenneth Crakian way of defining world model as an internal simulation of the world inside the brain.
Yeah, no, this is more general. This is a
Uh-huh.
way, one way of thinking it is this is a way of implementing an interface.
I see. Okay.
The
Yeah, I think
implementation can be internal,
this
can
is
be
really, I
external.
mean, this is to me this is different. This is just different from the way the term world model is used. So are you going to try to connect to that other is this like
The,
is it more
the other will be
general
a,
that
yes, the other will be a one subclass of this.
okay, okay, then let's wait until that point.
Mhm. Great, very good question. Thank you. So to start warming up on getting a sense of how this word model work, one question you could do is, could we, for given interface, could we have a trivial word model? A word model that is equal to zero. Like the state is always constant, is nothing. And you can prove mathematically that trivial word models correspond to interfaces that are memoryless. So basically, every action generates a observation, and that transaction is memoryless. So it doesn't matter what you did before, it only matters what you're doing now in order to see the consequence. Only those interfaces can be modeled by a word model that is constant. Any other interface has memory. It means what you did before will affect how what I'm doing now will translate into the next observation. And then the word model need to keep that into account. So word models are not arbitrary, and there are kind of lower bounds that you cannot go below. The trivial transducer would be the simplest word model you could think of, but that is not compatible with arbitrary interfaces. The trivial transducer only works for memoryless interfaces. Another question you could make is, what about defining my state of the world as my current observation? That would be equivalent to full observability, like MDPs. Under what conditions can I do that? Well, there is a Markovian condition that you can say the next observation depends on the previous observation and the previous action and nothing else. And so there is something about Markovianity of the actions and observations themselves that determine whether I can identify word model with the last observation, kind of MDP-like. So what we're seeing with this is that the state of the world is not arbitrary, has to take into account all the memory. It can be zero if the interface is memoryless, and it can be sort of trivial if the interface is Markovian, and is particularly more interesting for non-Markovian interfaces, so more like POMDP kind of examples. Now, here, I hope this slide is useful. So here we have four types of word models. In the top left, we have the full word model with all the dependencies. In the top right, we have one type of POMDP, where so in POMDPs you always have to define action T, observation T, which one happened here first, which one happened after. So in this case, there's a POMDP where the action happens before the observation. And there is one arrow missing, that is the arrow from the observation to the next state of the world, right? And why would you not want that arrow to be there? Well, if you have a classical world, you don't want what you observe to affect what will happen physically, right? You want the observation to be, okay, I observed this, but the physics are not going to change because I observed this or that. So that is the kind of thing that POMDPs guarantee. Your observations don't that affect the future evolution of the environment. There is another POMDP, that is the one below, that has the indexing shifted. So here the observation at time t happened before the action at time t, but otherwise is equivalent. And you can, if you have an interface, you can swap it and you get from one to another. So these two things at the right are basically the same and are basically what are POMDPs. And as we can see, this is a particular type of word model where there is one arrow missing or two, depending on the indexing. What is interesting is this other type of word model that we're calling here belief transducer. As you can see here, the arrow from the observation to the next state is present. And what does it mean? Why would I want that? Why on earth could I want my next state to be affected by what I observe? Well, you would want that if the world model is capturing knowledge, not physics. And that's why we call it belief transducer. So if you make the state of the world that is explaining your interface to capture the belief that you have, the Bayesian belief, for example, that is exactly what you want. You want your belief to be updated by the last observation. And that is what belief transducers or all the full transducer allow you to do. So I find this useful because you are kind of putting into a single template all these type of things. So belief MDPs, POMDPs, et cetera, et cetera. There are all types of these transducers. But depending on what you cut and what you don't cut, you get one or the other. And a belief transducer is something like a word model that an agent will be running. We're going to go more in detail later, but that is the type of thing that is computable. Well, and we will get into online computability later. Is this helpful? I hope. Good. And another thing that I haven't mentioned, for simplicity, we're going to assume that every variable is discrete, just to, not have measure theory problems. We're going to allow, in principle, for variables to, for example, to the states of the world to be increasing over time. This is not great. We're not going to be happy when that happens, but we're going to let it happen. And ideally, we would like to have word models with a constant phase space. That those are the good ones because those are the ones you can run. But in principle, we're not ruling them out by definition. So yeah, I think this is all the fundamentals we need. And with this, we can start cranking into minimization of words. So how shall we do this? The first question that we are going to think about is, for a given interface, is it always true that there exists at least one word model for it? Or could it be that there is an interface that is so wicked in statistics that there is no possible word model that is compatible? And the answer is there is always a little bit trivial, that we call Funes. I don't know if you have read Borges, the Funes de Memorias. So this is a word model that just remembers everything. And this works in the mathematical sense. So you are saying S is the vector of everything that happened before, and that will factorize things in the right way. This is a not very useful word model because, as I said before, the phase space is growing exponentially. So it's not going to be very practical, but it's good to know that it exists. Because with this, we can tell that every interface has at least one word model. And by this trick, we can we can kind of focus the question a bit more, and we can now think about reduction of word models. So if I have a word model, how can I reduce it? Instead of like just thinking minimality out of nowhere. So we're going to think we have a word model and I want to shrink it as much as I can. How can I do that? So to think about word model reductions, we're going to think of coarse grainings. So we're going to take a function that goes from a state S to a phase space C that is a bit smaller. Hopefully, they're usually surjection. So we're going to cover the domain, but its cardinality is smaller. And we're going to define world reductions in a way that is sort of equivalent to bisimulation in POMDPs. So the coarse grain process we require that is still satisfying this graphical model. This is super not trivial. So for example, if you have a good behaving word model and you coarse graining to a constant, so you say you shrink it everything to the same state, usually you're going to break things. And we saw before that the constant word model doesn't work for most word model, for most interfaces. So we have to be careful. The number of coarse grainings that are compatible are not random. You have to choose the good ones. And there is a definition in the paper to say what are the conditions for the coarse graining for this to work. But there is one definition, and you can define in this way word reductions. So of all possible coarse grainings, some of them are good in the sense that they give you another word model. And in principle, you can start coarse graining, coarse graining, coarse graining until you cannot coarse grain anymore. We can also define isomorphism. So if one word model can be reduced and then the reduction can be reduced back into the first one, that means that we are just reshuffling labels, right? So now we have a notion of isomorphism. And also we have a notion of minimality. We start reducing until we reach a point that any reduction is isomorphic to herself. So with this, we have at least a theoretical machinery to start thinking about minimal word models. And now comes the big question. If I have one interface and I give you two word models that are different, and I reduce both of them separately, are you going to arrive to the same point or not, isomorphically? And of course, I'm asking this question because the answer is no, which was very frustrating. So the general situation is that by simulation on its own doesn't give you a single global minimum, which is very frustrating. It's like then is there is no simple minimal word model that you can just go and compute and be happy about it. What is the reason? Like intuitively, what is the reason? Um, the intuition. There is one construction that I find very useful. Imagine you have a word model. Let's say the word model has three states, and now you said you initialize your word model in state one, and you run different things. Different things happen, and you compute the probabilities of different trajectories. And you do the same exercise by initializing your word model in state 2 and in state 3. So now you have vectors of probabilities of things that could happen starting the word model in state 1, 2, or 3. And you have this matrix that as time grows, the matrix will grow, but doesn't matter. We have these sort of vectors of future events. By simulation tells you if two of these vectors are equal, you can collapse the thing without problem, right? And that's one way to see redundancy. It's like I would like my world, my states, to give me different forecasts for different things that could happen. I would not want to have states of the world that I'm differentiating, but for anything that I can see from the interface, everything looks the same. So if two states give you the same probabilities, that's not efficient, so I collapse them with by simulation, by coarse grainings. Now the question is, what if I have three states that I have these vectors, and the vectors are linearly dependent? But they are not equal. None of them is equal to each other, but they are linearly dependent. So their dimension is two instead of three, but it's not one. Then you cannot bisimulate that in general. Maybe there is no two states that I can collapse, but there is still some redundancy going on. And that redundancy you cannot get rid by bisimulation, and that's why bisimulation is not enough to get to like the optimal, most distilled world model. Now, what can we do about this? There are two options. Either we embrace the situation, we accept that worlds are not unique, minimal worlds are not unique, and that's how life is. Or we can go a bit crazy and say, I'm willing to deal with negative probabilities. What is that? What is that? How does that work? So to think about generalized transducers and quasi-probabilities, I like this example. I find it useful. Imagine you have this event with this random variable with three possible events. I think of it as a kind of a quantum coin. So the events have probability 0.6, 0.5, and minus 0.1. What is the meaning of that? I have no idea. But if I coarse grain my coin, if I cannot distinguish anymore events A and B, I can distinguish A and B versus C. Those are the things I can distinguish. Then from this quantum coin, I get a fair classical coin, right? Because I'm collapsing two states, I add the probabilities, I get 0.5, 0.5. Now, if my inability to distinguish confuses state events B and C from A, I will get an unfair coin. And by the way, quasi probabilities, they have to sum up to one, but the sum components can be negative. So my intuition of what a quasi probability is a source of randomness, but it's not a source that can be directly observed. You can observe it through cross grainings, and different cross grainings will give you different things. But the thing itself cannot be observed. And what one can prove is that the question about finding minimal word models is something like you have this is the probability of the interface, so the probability of a sequence of observations, conditional sequence of actions. This can be, if you have a word model, it will look like this. So it's like two vectors multiplying some matrices. And the argument is if you force these matrices to be stochastic, so non-negative and they have to sum up to one, then you have less freedom than if you allow the numbers in the matrices to be negative. So the optimization is more flexible. There are more room to try things by relaxing the condition on non-negativity. And that's why by allowing negative transitions give you more solutions and potentially better ones. And when you go to negative probabilities, you can use full linear algebra. So you can rotate things, etc. And that's how you can get rid of the redundancy of the three vectors that are linearly dependent. So there is a theorem that say generalized transducers can we always reduce up to a unique minimum. So any interface has one minimal or up to isomorphism, one minimal world model that has quasi probabilities of transitions that is minimal in the numbers of states. And then for that model, you calculate the probabilities by a formula that looks like the thing on top.
Can do you think we can maybe spend a little more time on these negative probabilities because I think that's a very interesting concept. And my first question is, did you invent this or does this exist in the literature and you just found that it's useful to your case?
Yeah, I found them. There are this literature is quite extraordinary. There are like 10 papers or
Yeah.
eight from
Okay.
starting from the 80s, but they are incredibly good. Like they
Okay.
are so thorough and so clean and beautiful, but they are like very few and they are
Hmm.
this kind of niche that nobody have ever heard of them. So there is a PhD thesis of a guy from MIT from the 90s, then there's another PhD thesis and a couple of papers. All of this in HMMs. So this
Hmm.
is a
Hmm.
HMM minimization. What
Hmm.
I did, I took exactly the same thing and I applied to interfaces that is basically the same, just with some conditioning. So I did very little, to be honest.
Hmm.
I
Hmm.
just basically took the ideas and I applied them to this context.
Okay, so this is very interesting because I mean, there are some theories that physicists have developed, like generalized probability theories that try to unify classical and quantum probabilities. This is different from that, right?
Yeah. Here,
And
here, there are no probability amplitudes. This is not
mhm.
quantum mechanics, to be
Okay,
fair.
okay,
There are no
yeah.
like to the power two or anything. It's
Hmm.
just
Hmm.
relaxing the thing to have more degrees of freedom.
Okay, but how do you interpret that? Like, does this fit any of the Bayesian or frequentist interpretation of probability? Like, what is the
This is my interpretation.
uh-huh.
So
Okay,
you don't.
okay.
You go for this if you want, if you are the architect of this agent and you want to run the interface so that you
Hmm.
can test the agent and you can, you want to have multiple rollouts and with as little compute as possible, you want to test it in many situations and you want to minimize the amount of compute you need for every rollout, you do this. This is an
Hmm.
algorithm.
Hmm.
You multiply these matrices, you get the right probabilities.
Hmm. Hmm.
One point of that is important is that the emission probabilities of the observations are always probabilities. Those are
Hmm.
clean.
Hmm.
The
Hmm.
things that are
Hmm.
messy are the transitions of the latents.
Hmm. Hmm.
So the trade-off is you cannot reason about the world in probabilistic terms.
Hmm. Hmm.
You cannot do law of large numbers, like any of that doesn't work. This is a black box algorithm that you crunch numbers and then you get the right emissions, and
Hmm.
that's it.
Hmm.
So in that sense, my interpretation is a trade-off between interpretability and efficiency. It's
Okay,
mostly computationally efficient, but you cannot say anything about how the world is doing anything.
I see. Yeah, it's okay. Just a useful method that allows you to get this nice theorem. I guess that's the take.
Yep.
All right.
And it allows you to run this with the least amount of compute.
Hmm. Hmm. Nice.
So in my head, this is one solution to the problem of word model minimization. And again, this is not a word model that an agent could use. Because in general, these word models cannot be computed on time. And I will go a bit deeper in a couple of more slides. But this is not a word model for the agent. This is a word model for the external person that is generating the sandbox to test the agent. And it's satisfying because there is a unique solution that is minimal, etc., etc. In principle, one could use this word model has an important property that is the number of states. And one could use that to characterize how strong the agent is, because a stronger agent will have more dimensions that are active, or so you could use to diagnose agents in some way. But the degree of diagnosis that you can do, I don't know. Maybe we haven't thought enough about it, but it seems that it's a bit less than what you could do with a proper statistical word model. Okay, so this concludes one question, that is how you minimize worlds. But it leaves us a little bit with a bitter flavor in the mouth of like, oh, but I would like to understand something. I would like to do more, and also I would like to understand how agents are building model for themselves, etc. So the next chapter is about that. How can we do more interpretable world models and world models that the agent could build? So for that, we are going to consider different subclasses of world models. One is uh, we can call it predictive. So here you have this mutual information term that says the state of the world at time t has no information about future observations that is not included in the past. H is the whole history, observations and actions, and future observations. So this is a basic requirement that you need for a word model to be computable. You don't want it to have some future information. To give an example that I find useful, imagine your world is like two, um, I don't know, some bit strings that are in some chests, and you run the simulation, and at time zero, those chests are decided. What are they hiding? And then the agent walks and then open one chest or the other. So the world model at time t has that information that the agent only will recover in the future. That is not predictive because the state of the world at time t has information about something that will be seen in the future that couldn't be anticipated by things that were seen before or actions that were taken before or after. So these are the kind of things that couldn't be computed by the agent until the agent see the thing. So that's a minimal requirement to be predictive. A stronger requirement is to say, I would like the state of the world to be a function of the history. And this is something like proper that the agent could easily compute, having enough compute. So basically what we're saying is the agent is doing stuff, seeing stuff, so there is a history, and maybe keeping everything in mind is impossible because agents are not finite. So we would like to have some compression with some function. So F would be the compression that keeps some part of the history in mind, that is S, and some parts will be thrown away. So an observable world model is something that could be computed online by the agent. The best type of world model for an agent is more than observable, because the weakness of an observable world model is that maybe you have been running for 1,000 years and now you run to 1,001. And if your model is purely observable, you might need to recompute everything from the beginning of the Big Bang, and that's not great. So unifilarity means that the world can be updated. So for a given state of the world at time t and the new observation and the new action, I can do something with that to generate the next state of the world. Not every observable world is unifilar, but every unifilar state of the world is observable. And the unifilar worlds are the good ones because those are the ones that are really like feasible from a computational perspective. One way to do this is with beliefs. So beliefs, as we know, once you have the belief at time t and you see the next action, the next observation, there is a Bayesian belief update formula that gives you what is the next belief. And that is exactly the type of unifilarity property. So we have a state, we have the next action observation, we update, we generate the next state. One thing there is a theorem that we have in the paper that says that if you take the beliefs as states of a transducer, that is a world model. So with the beliefs of an agent can be used to factorize the interface, which is not super surprising in the sense that beliefs are known to be sufficient statistics of the history for the future. So that's sort of is sort of the almost the definition of what they are. But it's also useful, and this is what I was saying before, that the same transducer structure also capture beliefs in MDP. It's the same thing, fits in a different way. And in that sense, I kind of feel that transducers are the type of world models because they capture everything and under the same formalism. So this is good. I really like Bayesian belief updating, and now we know that this is a way. One thing that Bayesian belief updating is very useful is that you start from a world that is not observable, but maybe you know about it. So there's a distinction between a world being observable versus you knowing how it works. Because you could know physics, but you still cannot see the whole universe, right? But because you know physics, you can have a belief. Let's say you have a uniform, and because you know how everything would have update if it happened, then you can do beliefs and you can update them. And this is the point at which we reach the kind of the standard view of world models, because here we could say there is the agent has an interface. The agent builds a world model that is whatever it is, and then it uses it to generate beliefs, and then where the is going to at the end be using what we call it the belief transducer in order to make actions and planning, etc., etc. So
Can I ask some clarification questions on this slide?
yes, please.
Um, that function B of t that accepts S of t and gives you the beliefs, can we think of that as the agent's inference algorithm? Is that your intended meaning?
Yeah,
Okay.
is a way that the agent is using a model to generate beliefs.
Okay. All right. So this is maybe trivial, but you probably discussed this earlier. But can you remind us why does that belief operate on S rather than the actual observations Y? The agent doesn't have access to Y, right? Is that the idea?
Uh, so here we're saying that B could be S.
Yeah, but I guess B could be a processed version of S as well, if you infer something. I'm just saying that why does B operate on S? I thought that like Y are defined as the observations,
Yeah.
but those are not the raw sensory observations that the agent gets to receive. The agent receives S. Is that the
No, no,
idea?
no. No. S is the state of the world that the agent never sees.
Yeah,
Y is
it
the
never
world
sees.
prediction that the agent sees.
Okay, then I think that this kind of deviates from what I thought this belief should operate on because the agent always gets to see the raw sensory observations. It
Yeah.
never sees the actual true state of the world, and the agent's internal beliefs also have no idea about those S. Maybe there should be some mutual information between the beliefs and the S. That's a good thing for the agent to have. But
Uh,
I guess the beliefs should operate on Y, the observables, not S. That's my what's confusing me.
I see. So the equation is not saying the belief is operating on S. The
Uh-huh.
equation is saying the belief is a vector and we're taking the S component of the vector.
Uh-huh. Wait a second. Okay, so this S does not map to the capital S, that is the blue
No,
variables.
it does map, but it's not an operation in
Hmm.
the sense that you put the S in and you get the B out. It's,
Mm-hmm, mm-hmm,
I mean it does, but this equation here is a
mm-hmm,
vector
mm-hmm,
equation that
mm-hmm.
we're taking one coordinate.
Okay. Yeah, that's still confusing to me because yeah, the agent never has access to S at all at any time, and it doesn't even know the dimensionality of S, right?
Well, here we're assuming that it does know the dimensionality of
Oh,
S.
okay. Okay, okay. All right. So
So,
it
but
does
it
have
could
some yeah, go ahead.
it could be wrong. The model,
Uh-huh.
the agent could have a wrong word model,
Yeah.
but it
Mhm.
has a word model. And
Uh-huh.
here we're assuming that the word model explained the interface. It could be completely not true in the sense that it has a different cardinality, it's a different alphabet,
Mm-hmm, mm-hmm,
whatever. But
mm-hmm,
it does factorize the interface. That's what we are assuming.
mm-hmm, mm-hmm,
Then we are not assuming that the agent can see S. The
mm-hmm,
agent believes in S, so it
mm-hmm.
believes that this is true, even if it's not true.
Ah. Hmm.
And
Hmm.
there is some prior distribution on S,
Mm-hmm, mm-hmm.
and then you update that prior distribution.
Wait, okay, so this is a great point because if you define S in that very sense you just said in your last sentence, then
Mhm.
S is completely the latent distributions inside the agent's mind. It has nothing to do with the world.
Yes,
Okay, all
absolutely.
right then.
Absolutely.
Never mind. Okay, that is yeah, that makes a lot more sense as a world model now, um, because A and Y are properties of reality. They're just kind of like real signals, and
Yeah.
then S is some belief state. It could be anything. It could have any dimensionality. It's agent dependent.
Yes,
Cool.
exactly.
Okay.
That's
All right.
exactly. And the whole spiel of the whole paper is that S is always a bit arbitrary.
I see. Okay. Okay.
It's a bit anti-realist in a way. Like there is no privilege S over other S as long as it explains the interface for the agent. The agent cannot tell the
Oh
difference.
yeah. That makes sense. Yeah.
Mm. So, and the process of belification, you're going from a model that you believe on, but you cannot see, into a
Mm-hmm.
model that you can actually see, because the beliefs, you can see them,
Mm-hmm.
and
Mm-hmm.
because they are your beliefs.
Mm-hmm.
And for example, the first belief at time zero could be a uniform, and then given what you observe and condition on the world model that you believe on, you update the belief into another belief,
Mm-hmm.
and this becomes, this is a new transducer of the same
Mm-hmm.
interface. But what
Mm-hmm.
is sort of interesting is that you're turning a transducer that is not observable into
Mm-hmm.
a transducer that is observable and unifilar.
Mm-hmm. Mm-hmm.
And that's the whole process of going from a POMDP to a belief MDP.
Mm-hmm. Yeah,
So,
it
so
seems like also like another way to say this is that you want to design an agent that has good properties, and observable and unifilar especially is a good property for the generative model that defines the agent.
yeah. So
Hmm.
I'll tell you something funny. When I was thinking about this, I thought that I could generalize based on inference
Okay.
because
In what sense?
I thought any word model that
Yeah.
is unifilar
Yeah.
for a given interface is kind of a Bayesian inference.
Mm.
But you could have non-Bayesian inference by doing this.
As in like, okay, if you want to say like generalized Bayes rule, as in like, you have different exponents between the prior and likelihood, or, is that the sense at which you were thinking about it?
Uh, I thought anything that is like B, that
Yeah.
formally the only thing you're requiring is that it factors the interface and
Yeah.
is unifilar.
Yeah.
Anything that looks like that, you could think is a belief.
Ah, wow. Okay.
And then I
That is
thought,
pretty
this is
interesting.
so general and so beautiful. Now I have this general
Yeah.
theory of beliefs, and that's great. And
Yeah.
and and was I really hope maybe in some cases some weird beliefs are going to be better than Bayes, and that's what I thought.
Yeah.
But you will see the
Yeah.
answer.
Okay. So it turns out that Bayes is the most general thing you can have.
Let's wait. So that's
Okay.
coming
Okay.
in 2 slides.
No spoilers. Okay. Okay. Let's
Yeah.
keep going.
Okay, but good, very good questions. So yeah, this is where we are. Now, next question. The next question we want to think of is for doing this process of vilification, you need a model. You need to believe in a world. And what if you are very you have very little creativity, so you cannot come with a world, you can just see things. Could you somehow bootstrap a world model out of the observations themselves? And there is this comes, I came to this from a literature called computational mechanics. And the idea here, this is the example for macro processes, sorry, for time series without MDP actions. So the idea here is for a given, this is not Markovian, for a given time dynamical process, we are going to take histories. So this is X, our arrow to the left is past, arrow to the right is future. And we're going to say two histories are equivalent if their prediction for future events are the same. And so we can build equivalent classes of histories by doing this, which is called E. So the epsilon equivalence is that if they have the same predictive ability for anything, and then you can take for a given history, you can apply this function, and so it's a kind of a coarse graining because you're grouping a lot of histories together. And with this, you build a variable that we can call it E. And the whole story about computational mechanics that is very nice is that you can build kind of an HMM out of these coarse grained histories. So here the drawing is we have a binary process, maybe very complicated, very non-Markovian, but we take different histories, and if they have the same forecasting probabilities for every future, we say they're the same. If they have different forecasting, we say they're different. And the result says that with this, you can build an HMM that is minimal for under some constraints, as where these equivalent classes are the latent and the observations are the next things. So this is a way to kind of bootstrap an HMM out of thin air. You just have data, but you are grouping the histories and you say, this is actually my latent, and this works as an HMM. Does it make sense what I'm saying? It's a bit of a funny construction, but it works. Is one way that builds HMMs. And the idea here was to use the same construction for interfaces. And this was not invented by me. Actually, I found out later that this is something called the predictive state representation in RL, for anyone that have heard of PSRs. So the idea here is that we take histories of actions and observations, and we say the equation here is a bit more complicated because we have histories, the conditioning is on past histories and in future actions. So we have to condition on future actions also. And we say two histories are equivalent if the prediction for the probability of any future observations are the same. And then we're going to define a coarse grain function that takes a history and gives you this equivalent class. And in the literature that I was familiar with, these are called epsilon transducers, but in the RL literature, these are also called predictive state representations. And this coarse graining has a lot of very interesting properties. So the first property is that this is a transducer. This is not trivial, but the M, if we take M as the state of another process that is interesting to consider, you can prove that this factors the interface in the right way. So it's a word model. And another thing that you can prove that is intuitive, I think, is that if we take the Funes transducer that we know is a transducer, and we minimize it by simulation until the point that we cannot coarse grain anything further, we're going to get this thing. So basically, we are identifying any. So first, we keep in memory everything, and then we say, what can we identify of these things that we're keeping in mind? Because maybe we're keeping too many things in mind. And we merge everything that we can, and we stop when we cannot merge more things. And it's not so surprising that by merging in a careful way, by this kind of condition, we keep the condition of being a transducer. Now, what is surprising is the next finding, that is not my result, by the way, uh, is to say that this thing is the minimal bisimulation of any predictive word model that generates the interface. So just to go back to definitions, so predictive here, predictive is any word model that has no future information, and that is more general than being observable, that means a function of the history, and is more general than being unifilar. So basically, this result is saying any word model that the agent could compute online can be reduced to this thing called the epsilon transducer. So the epsilon transducer is the only minimal word model that an agent could compute online. And this thing updates with as Bayesian beliefs. So this is also kind of Bayesian inference. So this is a result that was like 10 years older, but it was in a different context. So the only thing I did here was to generalize it like an epsilon, like very, very tiny, and basically put it in a different context. But this is an old result. Now, what are the implications of this? I find these implications quite interesting. The first is the epsilon transducer contains all the predictive information about the world that is learnable from the interface. So anything that the agent could learn about the world, anything that can be learned is in the epsilon transducer. So I think that means that the epsilon transducer has very useful information in order to assess capabilities of an agent. This is telling you, if the agent can see this and that and do this and that, this is the upper bound of things that the agent could learn. The kind of things of the world that the agent can understand how it works and could modify, could affect, etc. Anything that is not in the epsilon transducer is not accessible to the agent. And so this is kind of putting an upper bound. If the agent is optimally smart and do everything in the best possible way, this is the kind of things that the agent can reach. So, and I would like to think that this is very useful for capabilities, assessment of capabilities. So if you know only the interface, you don't know how the agent works, etc., this is putting an upper bound on how far the agent can go. Is it clear? Second conclusion that is also kind of funny and interesting. If we have, let's say, two agents with the same interface, but different beliefs, different world models, let's say, for the sake of argument, we have two humans and they believe in different metaphysics. One has some weird religion, one has some other weird religion. So they observe different things. Their interface is sort of equivalent, but the world that they impute that is responsible of generating observations as a consequence of their actions is different. Because of that, their beliefs and their based on inference, etc., is going to be different. However, this is saying both Bayesian processes can be coarse grained into the same thing. that is this. So I like to think, like in a little bit on a playful way, that the epsilon transducer contains what are empirical facts, like scientific facts, like things that we can agree on. And anything else is metaphysics. So this is kind of a formal way to define what is metaphysics and what is not metaphysics. So anything that can be learned and is objective, and any agent with that interface has to agree on, is contained in the epsilon transducer. Anything that goes beyond that is not in the interface really, is something that you are bringing to the picture, and then you have to agree to disagree because this is not from, you don't get that from the interface. So it is, I find it very useful in a way to delineate what is empirical fact and what is not.
Can I ask what is epsilon exactly in this definition? So I thought, like, why do you even introduce epsilon? It's just there's it doesn't appear in
Yeah,
any of the equations.
definitely. That's a historical thing. It's a
Okay,
purely historical thing. Yeah.
maybe there wasn't like epsilon ball where you probabilities
So
are like within the.
the epsilon transducer is a generalization in computational mechanics of a thing called the epsilon machine.
Aha.
And the epsilon machine, I think the first iterations were continuous, and it was a bit like approximating Kolmogorov-Sinai entropy in chaotic systems, and then you have some epsilon balls that were going to zero or something. So
Hmm.
this is a historical thing, the
Hmm.
terminology.
Okay. Um, I mean, this result looks really powerful. And I wonder, is this epsilon transducer something that is practical that you can compute for a given setup? Are you going to talk about that a little bit?
Yes. I
Okay.
think in principle, for most realistic settings, it's not computable. It's
Hmm.
completely very hard. But
Hmm.
the rest of my talk actually is about coarse graining
Hmm.
and factorization.
Okay. Then, okay, but maybe before going there, maybe like at the conceptual level, I think both conclusions are very interesting. What conclusion two brought to my mind is that if agents have the same interface, can we think of this as agents having the same Umwelt? Is that similar?
Yeah, I would think so.
So like the
I'm
same,
pretty sure. I think so without having thought too much about it, because I know people that have spent their life thinking about Emerald. They have very
okay,
strong opinions of different sorts.
okay,
But I think to some degree it gives you a good handle into that
hmm,
100%.
hmm, okay, cool.
Any other question? Shall we continue?
Let's keep going if there are no more questions.
Mhm.
Hmm.
So let's wrap up what we have so far. The first thing we have is that so the first is a distinction between interfaces and word models. So they're not the same. Interfaces, as you had said, they are kind of real, and word models in this setting, they're not real necessarily. They're whatever that fits the requirement. And so the distinction is that for a given interface, there are many word models that are compatible. That's the first point to take home. Like there are surprisingly many, it is a very rich class, how many word models can be used for a given interface. The second point to take home that I find is also very interesting is that there is an intrinsic trade-off between computational efficiency and interpretability. So if you want to go to the wormhole that you can run in order to generate the next observations at the minimal computational cost, you're going to end up with negative probabilities, and that it seems to me that it will sacrifice a bit the interpretability that you can have out of that. And on the other hand, if you want to compute word models that the agent could learn in its own head in the standard way of word models, then it's not going to be the most efficient word model. You can use it to generate the next observation, but it's not the most efficient one. And it's sort of interesting that you have this trade-off between these two things, and that there is no way around it. You have to do. So there are many world models, and you should better be clear on what are your priorities because you cannot have everything. And this is a wrong conclusion because I didn't talk about reverse transducer. So those are the main take-home messages. And the rest of the talk, let's see how far I can go, is what can we do in order to make this a bit more practical? Because this is a very nice theory. It kind of delineates the boundaries of the discussion, what is possible, what is not possible, is conceptually useful. But of course, you can compute this for very toy models. If you look in the literature, there's a lot of work on computing predictive state representations, which is the same as the epsilon transducer. And there are linear ones that are computable, and so there are many techniques. So there has been a lot of work. But of course, if you want to do this in robotics or something like that, then it completely blows in your face. So in my view, if we want to get traction with these ideas in a more practical setting, is we have to find ways to coarse grain. That means keep only the essential part of the epsilon transducer or the beliefs, etc. Or and we also need to exploit factorization, and that is what I will present some recent work we have been doing on those things. So the first component is about how can we use symmetries in order to reduce the beliefs and these interpretable world models. So this work comes inspired by cybernetics. I don't know if you're familiar with cybernetics. Cybernetics is this very ambitious research program that happened in the 40s or 50s, and it was very ambitious. They want to, dominate the world in terms of feedback, and there are many like at the end it didn't work. It kind of break down, but it generated the seeds for many things that we love today. So there is a lot of disciplines that you can trace them down basically to cybernetics in one way or another. So there were many good ideas. It didn't play out as a world domination plan, but a lot of good things came out of cybernetics. Now, there are some ideas that I find really, really interesting from cybernetics. For example, the principle of requisite variety that says any controller need to be as the controller need at least the same degree of diversity as the thing that wants to control, or the good related theorem that say every good controller needs to have a model of what is controlling. All these ideas are really interesting. They're very attractive. When you start getting into the papers and the math, it's a bit of a mess. It's a very mixed bag. But I would say one take home for me is that a kind of the essential question that I see here is to what degree the agent beliefs need to reflect properties of the world. This is a question that I find super, super interesting. So if the world has some structure, to what degree my beliefs need to follow the same structure? And this is a question that I want to explore here in terms of symmetries. So the property we're going to study here is about like hierarchies. So in the case of physics, we can have hierarchies in the sense of you can have like, I don't know, atoms and then molecules and then, I don't know, organs and then societies. And so you have all these layers of reality and each of them operate in their own, they are self-consistent to some degree. Like you can do architecture without knowing quantum physics and works, right? And that's good because if not, every architect should study Schrödinger equation and etc. So in reality, we see this separation of scales. And kind of the question is, to what degree the word model of an agent needs to have the same kind of separation of scales, and can we think of that as abstractions? So to think about this question, one useful idea is to think of symmetries, in particular, the notion of invariance and equivariance. I hope you're familiar with, but just to remember you. So invariance is things that end up in the same place. Equivariance is things that end up in a different place, but if you switch the things, the destination also switches. And we're going to apply this to dynamics. So what does it mean to have invariant dynamics? It means that different initial conditions end up in the same point. What does it mean to have equivariant dynamics? It means that if you switch the initial conditions, you put forward, and if you switch back, you haven't done anything. For example, imagine you have a physical system with equivalent particles. So you have an initial condition, you switch the particles, and you let it run, and you switch them back, and everything works. So these are, the point is that invariance is a very strong condition, too strong usually, and equivariance is a much more practical thing that happens very often. And that's why it's useful to think of equivariance more than invariance. So the first result from this little paper from last year is to say that if you have a Markov process, which with equivariant symmetries, you can use the symmetries to coarse grain it and get Markov processes as well. So for example, in this is a very toy example, we have a Markov process with 6 states. You can see there is drawn in a way that the symmetries are very clearly the symmetries of a triangle. And a triangle has a group of symmetries that is showing in the middle. And groups are nice because they have subgroups. And you have the lattice of subgroups there. So in red, you have the rotation. So three operations, that is the rotation of the triangle. You have the three reflections of the triangle. And in top, you have everything together. And their theorem says every symmetry gives you a coarse graining. That gives you a Markov process that is a simpler version of the original Markov process. Important to say that most coarse graining or Markov processes are not Markov. This is sort of the intuition of POM-DPs. Like if you coarse grain an MDP, you usually don't get a POM-DP. And sorry, if you coarse grain an MDP, you usually get a POM-DP, and that's bad because it's very complicated. And the coarse grainings of an MDP that give you an MDP, those are good. So in the same case for Markov, coarse grainings of Markov that give you Markov, those are nice, but they are rare. And this tells you symmetries give you those. And not only that, it gives you the hierarchy of them. So here you can see how the triangle gets collapsed in different ways depending on the symmetry you're taking. And this gives you four different coarse grainings that gives you description of the process at different levels of resolution. This is the first result. Now, and we have, okay, so another example, Hopfield networks that I guess you're familiar with, the recurrent neural networks that has these attractors that can retrieve memories. So for example, here we train the Hopfield network with three letters. And the claim is that there is something called Matisse magnetization of the Hopfield network. That is a dot product of, in this case, we have three potential targets, the three letters. And you can, for a given initial condition, maybe that pattern in the center, you can take the dot product of the current configuration and each of the targets. You dot product, you get a number between 0 and 1. And the claim is that that is Markov process. And so the original Hopfield dynamics is Markovian. But if you now track only these magnetizations, you're going to have one magnetization per target. So you have a three-dimensional process now, but that is Markovian. And what is important is that those information is what is telling you what is going to be retrieved. Because if you flip to neurons, but the three magnetizations are the same, you can prove mathematically that the probabilities of retrieve any of the three patterns are going to be exactly the same. So basically, you're simplifying from the level of neurons to these three indicators, each of which is telling you the likelihood of retrieve that pattern. And that feels like a very useful simplification. Now, what is interesting is that you can build more symmetries into the system by training data. So now we train it on the three letters and all the rotations and reflections. And now you get a lot more symmetry. So the first course training you get is the magnetization one. But then every symmetry of the training gives you more course training that you can apply. And if you go to the highest point in this in the course training, you're going to get an indicator that is what is the letter that you might retrieve. I don't care if it's rotated, reflected, etc. I take the simplest one. So this is just one example of how you can use this to build coarse grainings. But let me go to the core point for this talk. The core point here is this is a second theorem that says if your physical process has symmetries at multi-levels, but now if the measurement process, let's say this is an HMM, if the measurement has the same symmetries, then there is a way to coarse grain the observations and coarse grain the latent to get a new HMM. And now you can do based on belief updating on a coarse graining, not on the full thing. So, and this is a way, let's say you have a super high dimensional belief that is impossible to update computationally because there are trillions of states. But this tells you if you have the right symmetries, you can start tracking a simpler, you're not tracking the full world, you're tracking a coarse graining of the world, but you can do that in a much lower dimensional world. Let me give you an example. Here
Wait,
we
can
have,
I, sorry, can I ask you a question? So,
yeah.
I mean, this is beautiful. I mean, I wonder if this is possibly related to the idea of renormalizability. Like, do you have that kind of result in here, or it's a different way to think about it?
What kind of result do you mean?
So, I guess in the physics sense, if a theory is renormalizable, then if you apply coarse graining, um, the mathematical object that defines the dynamics of that system does not change. It's just the parameters of that mathematical object, like the partition function or the Lagrangian. I wonder if this is also like, do you have the same structure or does it change?
No, so this is a bit different because what you
Hmm.
have in physics, you have infinite systems. So
Hmm.
first, you have like an infinite spin model.
Hmm.
You coarse grain it, but you get another infinite system.
Hmm.
If
Hmm.
it's finite, it doesn't work because you cannot
I
have this,
see.
right?
Yeah, yeah, yeah. Okay.
So this is for finite processes.
Hmm.
So it's a bit different in that sense. Another thing that is sort of
Hmm.
interesting is that normalization is this very strange like thing that is a mix of very fundamental thing with super heuristic. So nobody will tell you how you should coarse grain in
Hmm.
renormalization.
Hmm.
Like, oh no,
Hmm.
it's neighbors because that's sort of normal. But
Hmm.
they don't tell you where you get that from.
Yeah,
So
yeah.
one thing that I find beautiful from this is that this tell you asymmetries tell you how to coarse grain.
Hmm. Hmm.
So
Well,
that's another.
okay. I would guess that probably in high energy physics, that's what they do as well. Like the symmetries of the Lagrangian determines how do you do it. But the Wilsonian, like this spatial kind of corkscrewing, that seems like a little bit heuristic. So I get it. Yeah.
And another difference is that the normalization, at least the simpler versions that are the ones I understand the better, they
Hmm.
are space and they don't take into account dynamics so much. This
Yeah.
is intrinsically about dynamics.
Yeah. Yeah. They think about partition functions. The dynamics is more like a high energy version of that. Yeah.
Yeah, so usually it's about
Okay.
like equilibrium systems. So it's like you lead the equilibrate and then yeah, but it's not so much like past and future and all of that.
Yeah.
It's all about dynamics. So it's a little bit different. I don't fully understand how they're related, I have to say.
Hmm.
And I'm very interested in figuring that out, but I think they're slightly different.
But this is like the slides is from the same archive link that you put in a few
Yes.
slides ago. So okay, then
Yeah.
I'm gonna check it out. Yeah.
So an example to concretize all of these ideas a little bit. So here
Hmm.
we have a physical system. You have gas particles in between two chambers. And we're going to, for every particle, we have a binary indicator that is a down or up. So our state of the world is a binary string, which is white or black depending if the particle is up or down. And this is an old model from statistical mechanics that the dynamics are Markovian, and at every time point there is a probability of the particle to switch to the other chamber randomly. That's it. It's super simple, and it's used for studying like thermalization because if you start with all the particles in one chamber, they're going to distribute until you have like half and half and fluctuations around that. So that's the way it typically is used. Now here we're going to introduce one thing, that is we're going to measure the particles one by one with a little bit of error. So the observer cannot see the particles directly. The observer will see a vector, but that vector is a slightly error version of every particle, and you don't know which are an error. And the question is, how can you use those observations in order to learn back what is the state of the system? Um, if here in and I have the belief updating of the full system versus the belief updating of the symmetries. So you can see below that the number of states is quite high. This is for 8 particles and it's like 200 something. If you have 40 particles, forget it about doing belief updating. It's like, there, whatever, like impossible, completely impossible. So this is a system that you cannot really do belief updating of the full microstate. So what do you do according to this theory? Well, you figure out that you have permutation symmetry. You can exchange particles and the thing doesn't matter because the particles don't have special properties for being the first or the second. Then you realize that the orbits of the symmetry, that means the states that you can jump to another by symmetries, correspond to how many particles are in the bottom or in the top. So the number of particles. And that tells you that, and this symmetry is compatible with the measurement. So all of that together tells you, well, try to infer how many particles there are in each box. Don't forget about which is where, because that's completely impossible. Just track how many particles there are in each point. And then you get belief updating as the upper part, which is in this case, you have 9 states because you have 8 particles. And the idea is that that belief updating is much nicer in the way it scales with the number of particles than the one below. The one below it scales exponentially, so you cannot do it with 50. Here, for 50, you can do it perfectly fine. You are going to have 51 states. You can do it perfectly fine. So the strategy here is don't do approximated Bayesian inference of all of that. That is what people normally do. Instead of that, change your target of prediction. Be humble. Don't try to target the whole thing, target some aggregated thing, because most likely you don't care about particles if you have so many of them. And then do belief updating on that coarse graining, and you'll be fine. So that's the idea here. And the interesting conclusion is that we see that the system itself has this hierarchy because it has dynamics at the micro level, and then we have these dynamics at the macro level that are Markovian. I haven't proved that, but it's a consequence of the first theorem. So the dynamics of the number of particles are a Markov process that you can track on its own. And this is kind of the idea in thermodynamics, that you have the macro variables that are self-contained, that supervene on the micro dynamics that are very complicated. And then this structure of two levels is mirrored by the belief structure that tells you you have micro beliefs that you could update them and with a lot of pain, or you can coarse grain your beliefs and then update the coarse grain beliefs. And that also works. So the beliefs have these two levels that mirror the two levels of the object that you're studying. So this is the way this works with the symmetries. I'm working now on an extension for POMDPs, and in POMDPs the same works. So if you have a POMDP with the right symmetries, you can build another POMDP that is much smaller. And you can do belief updating on a much smaller space, and then you can do control. And depending on if your reward function depends only on the coarse grain variables, then you're good. If not, you make some errors. So here I have a little example about that. So we have kind of the same system, the same particle, and now you have an agent that, let's say at every time point, there is a good chamber and a bad chamber, and you want to start pushing particles to the left or to the right. So at every time point, you see the agent C, which is a good part of the chamber, that can change with some probability. And you have an action that is you choose a particle to push it to the left or to the right. That's what the agent can do. And then you run the agent is the orange, and for few particles it does, sorry, the full agent is the blue. So for little particles it does very well, for a lot of particles that horribly bad. This is tabular Q-learning, and the problem is that if you have 40 particles, you have 2 to the 40 states, so you will never see the state twice, so you cannot learn the Q function. Now, if as an agent you say, okay, forget it, I will just track the number of particles instead of the actual particles, and then I will push particles because I cannot see them anymore. I will, instead of having a linear number of actions, I will just have two actions, push a random particle to the left or a random particle to the right. Now you switched from having an exponential number of states and a linear number of actions to having a linear number of actions and a constant number of, sorry, a linear number of states and two actions. And then this macro agent is a bit worse than the other one for very few. This is just the way I set it up. I set it up such that in the macro case, you push a random particle to the left or to the right. And it could be that you're pushing a particle that was already in the other chamber. So you can waste actions, and that's why for small, the micro agent does better than the macro agent. But you can see in the 40 that in the agent still learns pretty well, while the other agent doesn't learn at all because the table that is trying to learn is just crazy large. So this is a super toy model that I tried the other day. I'm working on this at the moment to make it a bit richer. But this is one idea on how this can be used in order to build abstractions for make big POMDPs more tractable or MDPs also. This is an MDP actually. This simulation was without the observation noise or anything. So this is one type of idea. Let me walk you through very quickly about the rest, and then we can have some free discussion. So another idea I was thinking for very long is how can we build abstractions with rate distortion theory? Because that feels very natural. Like maybe if I want to do by simulation perfectly, I cannot by simulation too much. But if I can afford a little error and I can get out of that a lot of compression, I should do that anyway. So how could we do that? This is a very recent paper that I'm finishing now. So the idea here, the first move is to have soft state action abstractions. So if you look the literature overall, most the first kind of thing is to do a state abstraction where you compress states. Then you do state action abstractions where the constrainings are joint, and then you have all these equivariances, etc. And here the idea was to have soft compression. So instead of having coarse grainings, we have stochastic encoders and decoders. So you build this encoder, the decoder, these are two kernels, and with that you build a new MDP, that the rewards and the transitions are there, as you can see. But they could be unfaithful in the sense that you can be making a lot of errors. And you might be, so below I have these operators to push and pull value functions up and down. And depending on the encoders, if you learn the optimal value for the simpler NDP, you push it down, it can be super wrong because the encoders and decoders are completely arbitrary in principle. So an interesting question is how can you measure that error, abstraction error, and how can you track it, etc. So the idea that I found is the following. There's a lot of equations here, sorry, but let me walk you through. The first is you might be familiar with bisimulation metrics. So bisimulation metrics is a way to put number. So bisimulation is when you have these perfect states that you can merge without any damage. The bisimulation metric is a metric that is zero if it's a pseudo metric. So there are different things that have zero distance. So if the thing is zero, you bisimulate without error. But if it's small, it tells you the damage you would make is small if you do it. So it quantifies the degree of difference, the degree of damage that you would make if you coarse grain. This is an old idea from RL, and there's a lot of work on bisimulation metrics. What I took here basically, so in the top, that's by simulation metric, very classic. So basically, you're saying for two state action pairs, you compute the difference in the reward. You compute some difference in their transitions. So these some kind of divergence or some Wasserstein or some kind of metric like that. Then you require the distortion function to be Bellman compatible. That means that for any value function, their difference is bounded by the divergence. And then you do some tricks because if you have a distortion function, you could take like, you can think like, what is the worst that you could make? You could take like the diameter of your space by taking the worst case scenario. That happens to be too large. There is a smarter way of taking a diameter. That is, you kind of you do something smart with the actions, and then you take the worst case on the states. And this is the Hausdorff trick. And then for the state, what you do is that you take a microstate, you push it up to the abstraction, and then you push it down. And because these are stochastic kernels, you get a distribution. So we call that the round trip kernel. So what happened with the state if you push it up and then you push it down? And the variance of that distribution will tell you a bit like how much error the abstraction makes. And long story short, for a given, let's say you are learning, the idea here is that you have a very complicated MDP, you compress it in some kind of arbitrary way. So now you have a small MDP, and now you're learning in your small MDP. I have a value in my small MDP, and I would like to know what happened if I push it down, this value that I have in my small MDP, how far is from the optimal value of the real MDP? And there is this inequality that says that error can be decomposed in terms of a learning error. That is, if I do one more Bellman update in the small MDP, how much difference I will make. And you, because the Bellman is a fixed point operator, you can tell that the Bellman updates are bounding how far you're from the optimum. So that's kind of how much you can still learn in your MDP. Then there is this other term that is how much the abstraction is messing up things because it's like breaking things when you coarse grain. And then the idea is that the total error is lower. There is an upper bound in terms of these two things. And then you can say that the errors I'm making can be learning errors because I'm very bad in my game that I'm playing. This sort of, so the way I think it, I have this very complicated problem. So instead of playing this complicated game, I will simplify the game. And then how bad I'm in my game that I'm playing versus how wrong the game is with respect to the real game. So these two things can be used to update the whole, to bound the whole error. There's a question there?
Yeah, Fernando, I can you just elaborate the Bellman compatibility constraint? Is that like a constraint on your um Yeah, I'm like, should I interpret that as just a bound on distortion that you simply have, and like the constraint and constrained optimization that you usually do in like, is that just a value, or is that saying more than that?
This is a property for the distortion. So you would
Right.
not like
So
to
how do
have
you in practice like respect that bound?
like yeah, so there is a kind of a standard metric that people use that is called the fixed point. The fixed point. The bisimulation metrics is something that you have an operator over metrics, and then you apply it many times until you get a fixed point, and then that is kind of a standard, very good distortion metric. But
That's in the space of distortion metrics, right? So the
yeah.
fixed point would be a distortion function.
Yeah, so it's sort of a funny construction. So you have let me remember. So you have an operator on distortions, and you feed in a distortion, you get another distortion, and then the fixed point operator of that functional, that is this fixed point distortion that has super good properties. So
Can you actually operationalize this with like, will you show any examples with
yeah, yeah,
this?
yeah. I mean, you can compute it for small systems, and you can just compute it. So it's hard to scale it up. I'm pretty sure there's no there is actually a lot of work from Pablo Castro and other people to how to compute this empirically in big systems. So yeah, there's a lot of work on all of this.
Thanks.
And that is the condition that because how on earth this is the condition that then lets you use the distortion in order to bound value error. That's why you need that condition. So the key idea from here, sorry, I did this slide very quickly, like yesterday, and that's why they're not very friendly. But the key idea is that you're playing this simplified game, and you would like to know how far are you from a good value. And the idea is that you can bound your error, your total error, in terms of how much error you're making in the game versus how much error the game is making because it's a wrong game. And the idea from here is that if now you have a hierarchy of abstractions from very coarse to very fine, then you could use this to adaptively adjust your abstractions. You can start playing a very, very simple game that is easy to learn because it's small, but it's making a lot of abstraction errors. And as soon as your learning error within that game gets to the range of the type of error you're making because of the abstraction, then you can decide, oh, I have to increase my thing. So the idea was to use this principle and to have a rate distortion, to build a rate distortion family of abstractions. So here what you do, you take a very standard rate distortion target where you are compressed. The component is compression, the rate of the state compression. The second is the compression of the action. And the third is this distortion metric that you use and you would like to minimize everything, and you have these Lagrange multipliers in order to balance what is more important and what is less important to optimize. One beautiful thing of this formulation is that it's very general and you can recover a lot of things from the literature. So for example, if the encoder is deterministic instead of stochastic, you recover standard coarse graining based abstractions. If the if you push things so that you want zero distortion, you recover by simulation. If you want like you don't want to minimize actions, then you end up with something that people call it's not exactly the same, but very similar to lax by simulation. If there are many types of abstraction families from the literature that you can recover from this formalization by considering different corner cases. Now, here are some experiments. These are three super classic RL settings, so four rooms, taxi, and dorky. The second panel shows the type of trade-offs that you get if you start playing with beta. So what I did here, I fixed lambda to be 1, and that means that you are compressing states and action the same. You're not prioritizing between them. So the only parameter is beta. So if beta is very low, you you want a lot of compression and you're going to make a lot of error. in abstraction. So that's a very simple abstraction. And as soon as you start increasing your beta, you're going to go up in reducing your abstraction error, but increasing the rate. So the cardinal, how much information you are letting through the abstraction. So you get this trade-off. And then we have this heuristic algorithm that starts with a very low beta. So you start playing a game that is very simple, and you're computing your Bellman updates. And as soon as your Bellman update reach the same value as the abstraction error, you switch to the next beta. So that you can see in panel C how you start from very little and you like dynamically increase your beta. And in the below that you can see the performances. The color lines are each of the points in the top panel from the different fixed abstractions, and the darker line is this adaptive one. So you can see that for every game, you reach the optimal performance after you wait enough. And the interesting point is at what point of abstraction you reach the optimal performance. So there are different betas that with the star there, that is the one that reaches the optimal performance. And in the table below, you can see that the degree of compression that you get is quite substantial. So here in the first column is the total number of state actions. Second column is the degree of state by simulation you can make. That means compressing pure states. And because of all of these examples are a little bit non-symmetric, then you cannot do state compression. So by simulation, you always get 100%. State action by simulation, like that is known as MDP homomorphisms, you get much more compression. And with this adaptive state, you always get better than the pure compression without error. And you get more or less depending on the problem in particular. But one thing that is sort of interesting is that you can also see how much compression you're getting out of the state and how much of the action. And that tells you how much information is important, how compressible your particular problem is in terms of states or actions. So for example, for 4 rooms, there's a lot of state information you can compress, not so much action information you can compress. In in taxis, it's a bit the opposite. So a lot of action information you can compress and not so much state. And in Dorky, it's a bit half and half. So this
So
is
can you explain what the different colors are? Are those just different seeds, or
the
is there a
which color?
comparison taking place here?
No, no. So in the panel B, you have different points in the red distortion curve, right?
Oh yeah, sorry. Yes, of course, yes.
So these are the
Is
different
there like
performance.
any comparison with like a standard, like a null model, like a basic Q-learning or
So
um,
these are all Q-learning, tabular Q-learning.
so I suppose the beta equals 0 is just recovers basic Q-learning without any abstractions.
No, large beta.
Yes, beta. Sorry. Yes, beta equals 20, I suppose, is
Yeah.
tending there.
So
Okay.
for example, if you see the door key, if you take the darker point, so that is beta equals 6, you can see that the thing learns and then it gets stuck. So it cannot go to optimal. Then if you see higher values, they improve up to a point and they can reach better performance, but not optimal. And if you have enough, like if you go to the clearer compressions, then you do get optimal performance because you basically have something that is very similar to the full problem.
Okay. Sorry, thanks.
Mhm. I find it also interesting. This could be used in order to regulate the capability of your agent also. Like if you want your agent to do good, but not so good because you're a bit concerned, you could also like dial the beta in order to control that. That would be another interesting application of this. So with this, I'm almost done. Let me walk you very quickly about factorization before finishing, if that's okay. So this is another paper we have in the archive last year. And the idea here is that let's say we have the whole beginning of the talk was all about transducers. And so the first question we asked was, if you have a bunch of transducers, how can you compose them? And the second question is, if you have a big transducer, how can you decompose it? So these are the two questions that we study in this paper. So for that, I will walk you very, very broad ideas here. The first is that these are different ways to express a transducer. So the left is that the transducer has internal state R, generate an output Y, and is fed by a process X. So for example, if the transducer is a world model, that means R is the state of the world, Y is the observation of the agent, and X is the action that the agent is doing to input into the world. This can be, and it has this alternative description, but let's focus on the network one. So this is a general formalism to compose transducers. This is very general. So here we have the action that is feeding into one transducer, and then the output of one transducer is feeding as an input of the second transducer. So the second transducer is receiving two inputs as two streams as an input. And this is kind of a general way to compose transducers. And we have all the math in the paper, but I'm just showing some plots. Then you can kind of consider what if I cut different arrows and you get different sub types of compositions. So you have serial composition. So you have one thing that fits into this, and then the output of this fits into the other. You have parallel composition. So either one process driving two transducers or two processes driving the same transducer. And if you cut too many things, you get boring stuff. For example, with this, you can study like a grid world that we all know. You can think of this as two transducers that are in parallel, right? Because if you go up and down, or if you go left or right, these are different things that are not interacting. So you could think of this environment as an action that fits into two transducers in parallel, and the two things then feed into a reward transducer that takes the state that you are and then gives you a reward depending on something about the problem. So these are interesting ways to take word models that are like one blob, and then you can spread them into parts and then reason about them separately. Another example we have, imagine you have a robot in Mars doing stuff, and then you could have like everything in the same big transducer that is all the environment of that robot, or you could factor the environment into subcomponents, and then you have much more structure to think about like where it's going, what is the state of the battery, what is the climate. So yeah, so that, and just this is kind of a very quick walkthrough. We have some algorithms that if we just start from a big word model, like this is the word model of the robot, then you can factor by stages until you end up with little pieces. And why can that be useful? Well, you could marginalize some of the pieces. So for example, for the Mars rover, during the day, maybe you can forget about some things and focus on some other things, like more where you are exactly, and think less about the battery power because you have the sun giving you energy or something. And then in the night, you can maybe stop and not do anything, and then you forget about the map and navigation, and you think more on maintenance and other things. So we have this first paper on this. It's a formal paper. It's more of a studying the mathematics on how to compose, how to decompose, and the plan is that with that we can scale because most word models are not blobs. They're made of parts that are interacting, and to the degree that we can model each of them separately, the whole computation of the word model become much more feasible. And with that, I think I'm almost done. Again, to thank my collaborators and to thank you for listening the whole thing.
Right. Thank you, Fernando, for a great presentation. Um, Questions from the audience? I have one about the rate distortion. So I was having a discussion with Mani actually a while ago that rate distortion theory is beautiful, it's elegant, and I think we'll really like it. Um, but the choice of the distortion function, it seems like it's arbitrary. Usually, there's no, as far as I know, and I think we're discussing Mani also, we couldn't come up with a principled way of choosing a distortion function. What are your thoughts?
That was the reason why I got into the thing.
Okay.
I used to think the same, but I think for RL,
Yeah.
the by simulation metrics is a very natural way of thinking about
Uh-huh.
this stuff because
Hmm.
Actually, there is a useful way. This operator that I was saying before about this fixed point, the operator is basically like the difference of rewards plus a Wasserstein of the
Mm-hmm.
transition, where the
Mm-hmm.
Wasserstein use the rate, the metric as an input.
Mm-hmm.
So one way to think of it is that you start this fixed point with the indiscrete metric. So everything is the same. And so the first iteration will tell you what are the difference in rewards at the present moment. That will be the metric. Now you feed that metric into the operator,
Mm-hmm.
and that metric will go into the buzzer sign. So
Mm-hmm.
basically, that is going to tell you what is and the buzzer sign is discounted by gamma. So then the buzzer sign is going to tell you the reward difference for the next step, and you're going to account for the current difference in reward. And you
Mm-hmm.
keep doing this, and eventually you are kind of taking into account reward differences on discounted future rewards.
Mm-hmm. Mm-hmm.
So that's why the fixed point is useful because it's a way of thinking of kind of a value difference from
Mm-hmm.
specific states.
Mm-hmm.
And in that sense, it feels to me that a simulation metric is a natural distortion metric in order to use ray distortion.
Mm-hmm.
And so I was kind of thinking of that, and then I came across with this way of decomposing with these two things, and then I got excited and I ended up writing this paper because on the one hand, this tells you one way to choose a distortion that makes sense, and then
Mm-hmm.
two, this not trivial way to kind of adjust. Because another interesting property of red distortion is that you have continuous beta. You can, tune
Mm-hmm.
quite continuously between things. So that was another useful property that these two things came together into one story.
Okay, that makes sense. Actually, do you mind going back to your slide where you define the distortion function? Just I want to understand that more deeply. Okay,
Yeah.
so the distortion function has two terms. One is on the reward, and the other is in the transition. So I already like that you have both. I was recently at a talk by Dilip Arumugam, who has done a lot of work on this rate distortion, like resource constrained RL, and he presented a particular work of his where he's used something like Bellman equivalence. So it completely discarded the transition model and it solely focused on the reward and the value. And I thought that that is limited because then you're not going to learn a world model that is generalizable across tasks. You're just overfitting, in a sense, to that particular reward function. So that is, I appreciate that part. But then you have this Bellman compatible distortion. You're saying that if my distortion function is that, the definition up there, which let's say I completely agree with, it's perfect, great. But then what does that equation, that inequality mean? Can you help us understand that a little better?
So basically, you have to choose a class of values, and then you're saying that for
Hmm.
any value function in that class, the
Hmm.
difference between these two things cannot be is going to be bounded by the distortion.
Um,
Can I ask a clarifying question? Like
okay.
my answer to Hadi's question, which is probably wrong, would be that the whole thing hinges on the new symbol, right? That you're
Mm-hmm.
basically that's the thing that you have a free choice over, right? That will
Hmm.
like that's the thing that you're ultimately that you're that that will determine whether or not you respect this particular bound. Is that correct, Fernando? Like, because new, if I remember correctly, was your the arrow going to the
Ah,
um
no, there's a typographical kind of clash. So this is
okay.
some kind of calligraphic B. It's not a new.
The
Okay. So it
divergence
has nothing
measure.
to do with that abstraction function, the encoder.
Yeah, so no, yeah, they look very similar, but they are different.
Okay. So
Okay.
okay,
So
that's
this,
unfortunate. Then
yeah, sure.
my question still, Hadi's question still stands, and I have the same question. If you can
Fair enough.
clarify.
So this is a class of value functions, like the class of value function that you are considering. I
Hmm.
think you can take that to be like any value function. Especially here, I'm kind of thinking of finite MDPs. So you don't have, I think this become very complicated when you go to continuous state spaces and all of that.
Hmm.
But here, if everything is discrete, I think you can let V to be like any function, any value function. and then that just makes a bit stronger what is the this is also not defining D. This is telling you what is a good D, what is a good distortion, right? So this is a condition that you are asking distortions to satisfy.
So is the divergence measure the capital D sub calligraphic V, that the thing that is multiplied with gamma, that also should depend on your class of admissible value functions?
Sorry, which gamma and which D?
So if you look at the distortion function, it has the reward dependent term plus gamma times a divergence measure, D sub
Yes.
V.
Mhm.
You're implying that the divergence measure should be also aware of your choice of
Yes.
admissible value function.
Yeah, exactly.
Can you help us understand that as well? Because I think that the transition probability maybe it could be motivated on its own. It's like a separate thing. It's a property of the world, and it doesn't matter how valuable things are to you or like
Yeah.
what kind of value functions you are possibly can have. I think
Mhm.
that should, it to me intuitively seems like that should be independent of the.
Yeah. No, the transitions are whatever they are.
Yeah, but the
Yeah.
divergence also should be, it should be something more global, universal, like a KL divergence or something.
Yeah, so so the for different choices of V, there are kind of universal choices of D. So
Hmm.
for different choices of value functions that you want to consider,
Yeah,
there are universal
yeah.
choice divergences that does
Hmm.
this that work.
Yeah, but why does it have to depend on V? I mean, all I'm trying to accomplish here is that separate these two questions,
Hmm.
understanding the world for the sake of understanding, just like pure learning for the sake of learning of the world, versus accomplishing a task that is encoded in that reward function. Because you have these separate terms, the reward absolute value difference plus gamma times the divergence, I'm thinking that it would be cleaner, I would assume, if you have a completely independent divergence measure that does not depend on your V.
Yeah, but for the derivation of the bound, you need the you need this condition. Like otherwise,
Right,
how
it
are you
comes in
going?
the second line. It can like your distortion function could be defined as an abstract thing, and then of course it has to satisfy this supremum bound, and then that's where it enters the game.
Yeah.
That part is totally fine, the Bellman compatibility. I'm just saying that the distortion function itself could be mathematically defined as an independent mathematical expression, independent
Sorry,
of V.
I'm a bit confused. So you're saying that you're fine with the requirement of the inequality,
Yeah,
but you would like the divergence not to depend on V.
exactly. Yeah.
But how I think that there could be cases, I haven't thought
Hmm.
about this too much, but I
Hmm.
think there
Hmm.
could be cases where you could take a divergence
Hmm.
that could not work for a given family of value functions,
Uh-huh. Okay.
especially for the continuous case. Like,
Yeah.
uh, if the supremum is very complicated and the space
Uh-huh.
of families is like very
Hmm.
wild,
Hmm.
then
Hmm.
it could be that a given divergence that you very much like, it might
Yeah.
not be that guarantee.
Okay, perfect. I'd love to see that example. Then it would be much more convincing because
Fair
the
enough.
reason I'm insisting on this is because I have a very sweet spot in my heart for KL divergence, and it's just like everywhere you look, it appears either forward KL or reverse KL. It's just such a universal thing,
Yeah,
and
yeah,
I
yeah.
would like it to just so I don't have to think about divergence measure. It's just KL for me all the time. And
So,
but here you're saying that no, it doesn't.
so there is in the literature, I
Yeah,
didn't go too much deep into this. Like I saw
yeah,
this is something that people have worked out and it works in
yeah.
practice, so let's use it. But
Hmm.
what I saw is that this construction of the fixed point that I was saying before
Hmm.
that I find really, really beautiful, it
Hmm.
needs the divergence to use the distortion, sorry,
The other way.
you need the divergence to use the distortion as an input
Yeah, yeah,
in
yeah,
order to operate on
yeah,
this. And then for
yeah.
that, the the how is it called the Wasserstrass does that trick, and the KL
Hmm.
doesn't
Hmm.
because the
Hmm.
KL cannot fit that in.
Hmm. Hmm.
So I haven't looked enough into the math in order to like really assimilate this,
Hmm.
like how why the KL doesn't work. Uh,
Hmm.
I would like to have a clear answer for that, but I don't.
Yeah,
But
it will be also a way for me to a learning experience where I can broaden my dogmatic view. But I mean, yeah, Wasserstein distance also appears in everywhere, like in certain um, Jordan,
but
whatever. Like there was a paper from 90s, like where they, yeah. Anyway, yeah.
so I think my sense from what I read of this literature is that the Wasserstein appears very naturally
Hmm.
in
Hmm.
in setting. Um, but yeah, like the papers are from Fern and others, and they are really. I think the thesis of Fern is like super thorough.
Hmm.
So
Hmm.
take a look on that, and they have all the derivations. And I
Okay,
don't
so
I don't remember seeing a discussion about why the Kale doesn't, but I'm pretty sure there might be something in there.
okay, great. I mean, there might be something. So this slide is from which paper of yours, or is it out there, or are you working on it?
No, it's not out yet, actually.
Oh, okay.
I'm happy to share the draft is almost finished. I'm working out
Oh,
the
okay.
appendices
Yeah,
and all of that.
yeah. Yeah, I'm very curious to see this, because it's just a very personal curiosity of mine. But I don't want to hijack, I mean, we're already 10 minutes past. If there is any more questions, let's have those. If there are no more questions, let's thank Fernando again for this beautiful presentation. And yeah, I'm gonna stop recording.